Welcome everybody, I'm Philip Swan. I'm the chair of this new session called Interplanetary Infrastructure. The idea of this session is to bring together people who are interested in anything to do with infrastructure that might serve to help us advance human civilization to other planets or into near space at least, but get off planet Earth. So I'm going to jump right on in. I'm the kind of the top guy, the principal engineer in the Atlantis Project, and I'll be presenting today on the relentless march towards infrastructure and where it might ultimately lead us. You think about infrastructure, the first thing you have to ask is, what is infrastructure? So before you read this slide, I just want you to close your eyes and imagine in your own mind what you think infrastructure is, and then let's see if it ends up on this list. So get an idea in your head, and then see if it's on the system works. So I would say, a lot of people think of it as a capital-intensive thing that leverages economies of scale. Some people think of it simply as something that's large or long inside, like a road or a railway. Some people think of it as being a dependable thing, available, reliable all the time. I think of a bridge as opposed to a ferry. Some people think of infrastructure as something that's more conservatively engineered, something that's less likely to fail than maybe a vehicle would be. Some people think of it as something they don't want to live particularly close to, like a highway or an airport. A good way to think of it is it's a public thing, it's accessible, it's shared, it's built by the people, for the people, so it's a way to spread, amortize or use our particular contribution to society for the benefit of everybody. So if you think about the internet, as I mentioned in my earlier talk, the part of the internet that is your part of the internet, all the undersea cables in the ocean is like 14 centimeters of internet, undersea cable. That's your portion. Everybody benefits from that because we share it. The definition that you can find online would be that it's an economic driver. It facilitates commerce or quality of life, and it's a foundation upon which the structure of the economy is built. But maybe the simplest way to explain it is it's just a long-lived asset, something that's reusable, for example. Some examples of infrastructure are highways, tunnels, bridges, water, sewage, buildings, oil and gas pipelines, and the internet. But I want you to expand this idea a little bit and think about infrastructure for space. Like, what would infrastructure look like? Something would be helping us get into space. Here's an example of a longer-lived asset. When you look at this is the Falcon 9 system, and ask yourself, what part of this is reusable? So most people realize the booster returns to the Atlantis, and the drone ship is eventually returned to the launch pad. That's reusable. And then the capsule is reusable as well. And then there's the fairings. If you'd asked on a mass basis, you'd say this is like 90% reusable, or on an engine basis, there's 10 engines on the system, not including the small Dracos and things. 9 of them in the first stage are reused, 1 is disposed of, so it's like 90% reusable. So we're already going to this fairly reusable architecture with the Falcon 9 system. Now, if I showed you this picture instead and asked you how much is reusable, you might adjust your estimate a little bit. I forgot about the launch pad and all the stuff on the ground that supports the launches. That's all obviously reusable too, right? So maybe it's not 90% reusable, maybe it's like 95% reusable if you're talking about all that stuff. And you look at other launch systems, even the completely not reusable SLS is in fact largely made up of reusable stuff. There's a lot of complex technology like this trailer thing on the bottom, I think they call it the launch, the mobile platform. That's been reused for years. I think it's built in the 50s. And then there's gantries and towers, lots of parts of this. The whole Kennedy complex is reusable. Similarly, you've got the Starship system, which right now is obviously aiming to be fully reusable. And obviously the launch pad is not very reusable yet. but you have a system here that's largely reusable. Like you think about the investment that's going into the launch tower. This is a larger investment. In fact, Elon has said that it's really roughly 1/3 Starship, 1/3 Super Heavy, and 1/3 what he calls stage 0, everything else. Now let's take a step back even further and think about, what about Kennedy Space Center as an example, right? There's a lot of land in there. So that's obviously reused, but it represents part of the cost of this sort of fixed part of the system, which I think of as the infrastructure part of the system. So if you look at Kennedy Space Center, there's 24 square kilometers of land, there's almost a square kilometer of building area, there's like almost 900 kilometers of roads in Kennedy Space Center, according to their site. So that's a lot of infrastructure. And then you think about the keep-out zone. So if you want to launch a spacecraft, there's a keep-out zone, which if you're inside it, you're in trouble. Obviously, Starship's an example of that from the recent launch. And that's actually 130 square kilometers. Now this is just for making sure you don't get hit by the rocket if it explodes. If you want to get into launching a rocket every day, for example, or very frequently, it's not just about the keep-out, the safety zone. You also have to think about how do you not devalue the properties of everybody who lives nearby this launch zone. So you're going to need to acquire even more land to have it be such that the people who live near your launch facility don't get woken up every day with a very loud launch. So Starship was measured at 210 decibels. Krakatoa, I just put one example here. Krakatoa, which is the volcano that blew up, and it was actually heard 4 times around the world. This time was so loud, that was only 310 decibels, so you get an idea how loud Starship is. I was thinking of putting a video up, but it was just too loud. Just lots of cracking sounds. It was really interesting. To get an idea of where we are in terms of cost. So this is the ISS Resupply Costs chart. The orange line represents the cost of the space shuttle over time, and you can actually see the 2 peaks are where the space shuttle, the 2 space shuttles crashed or burned up again. But at the bottom, you can see that when they were kind of kicking along and doing all right, the cost came down to around $60,000 a kilogram to deliver things to the ISS. Then if you look at the more recent commercial resupply systems, I think the purple line, the blue line I believe is all the different commercial resupply contracts divided by the amount of payload they deliver to the ISS over time. And it gives you an idea how this cost started up being pretty high and have come down over time. The purple line is just SpaceX, and you can see how they've come down over time. If you look at things Musk and Gwen Shotwell have said over time, which is those lines in the bottom, the dots in the bottom, these are statements they've made about how much the system would cost, and the actual cost from the Office of the Inspector General, from the USA.spending.gov site, and from NASA's press releases are the actual lines that are above. And that gives you a sense of what the actual price of running the Starship, or not running the Falcon 9 system is. Quick question?
Yeah, why aren't the 2 shuttle disasters equal in impact of cost?
Oh, I have no idea, to be honest. Yeah. I mean, to be honest, the first bump is probably inaccurate because the line fit that I did at that end of the curve was kind of off. So I think that you probably have to take that first bump with a grain of salt. There was just not much data there, and the line fit didn't work very well. So I think that might just be misleading.
The first time we built another orbiter.
Maybe, yeah. Now, starting from the idea of what is Falcon 9, that's where we are today, and thinking about where we're moving to, I'm here to promote the idea of infrastructure, and so I want you to think about what is it about the next generation, which most people agree might be Starship, or something like Starship at least, depending on who wins in the commercial markets. But what is actually transformative, and what is incremental in terms of this sort of approach, right? So let's go through the different things that are different about Starship and Falcon 9, say going to the ISS, like the Crew Dragon plus Falcon 9. So, well, you've got stainless steel, but it's probably very hard to read. Stainless steel's specific strength is 63 kilonewtons per meter per kilogram. Air-grade aluminum, which is used for the Falcon 9, is actually much better. It's 204, so it's about 3 times the specific strength. So I don't think the stainless steel is a transformational change. I think most people would agree with that. But the chemistry or the engine technology, well, if you look at the ISPs of the Merlin versus the Raptor, there's a small improvement on the sea level. The Raptor is like, I think, maybe 6% better on ISP, which is good. And the vacuum optimized Raptor, it's almost exactly the same. So as the Merlin. So there's not really a transformative change here. I think more of an incremental change in engine technology and propellants. The fairing strategy, well, the Falcon 9 jettisons its fairings and you can recover them out of the ocean. With the Starship, you don't even do that, you just take them all the way to space and they come back. But is that really a transformative or even an incremental improvement over the technology? Not really. This idea that you always return to the launch pad, we've already done that with Falcon 9, but it's not as efficient as landing downrange. There is the idea that Starship is larger, it's about 2.4 times as wide, which triggers the square cube log. You get a little bit more volume. So the tank material should require less tank material to hold the same propellant. But this is already canceled out by the stainless steel choice, so that's not as strong. So it ends up probably being kind of a wash. And then you got things like the grid fins don't fold. That's not really an optimization. There's no landing legs. That's a small improvement, but landing is probably not a big part of the total weight. So now we're down to the things that Musk always talks about, like it's fully reusable. So we talked about Falcon 9 being 90, maybe 95% reusable, if you include the infrastructure around it, and we get the extra 5%. And then we're getting to like rapidly reusable and frequently reusable. Now these ideas are essentially the same ideas as what infrastructure is about. Like infrastructure is designed to be frequently reusable and rapidly reusable. Think about a bridge. It's always there, it's always reusable. It's a technology that's based on the idea that if we have enough people to use it, it will make sense to build it. And I think this is fundamentally what Starship is really all about when we talk about lower costs. It's about this idea that it's going to be more like infrastructure.
What's the difference between rapidly and frequently?
Well, frequently more, rapidly would imply that, if you need to launch it 5 times in an hour, you could do it. Not that could be cheap, maybe 5 times in a day would be more reasonable. Rapid or frequently reusable means using it every day, like you're launching it every single day for an entire year because you want to go to Mars and then you send a lot of stuff. So that's maybe a different model, but there's generally Musk says rapidly reusable. So I think frequently reusable is really where it's going.
Saying one's an average and the other's a surge.
Yeah, the rapidly reusable implies that you can do back-to-back launches fast, and frequently usable means that you've got enough market share to actually fill all the launches for a lot of launches in a year. All right, so where are we trending with all this? Well, the next generations of technologies are going to require more land. They'll be in remoter locations because of the sound problem. Probably more concrete, definitely more concrete on the pad. More steel tanks, more complicated steel towers, and then a large fully reusable rocket. So, but the point here, all of this is sounding like infrastructure, a lot of concrete, a lot of steel, a lot of land, right? This is all infrastructure type terminology. All right, well, I was going to let Elon say a word.
To the momentum of the way things were done in the past, unless you think it this way.
Well, just as a function of inertia, people will want to use the same tools and methods that they're familiar with. That's what they'll do by default.
Yeah.
And then that will lead to an outcome of things that can be made with those tools and methods, but it is unlikely to be the platonic ideal of the perfect product. It's good to think of things in both directions. So like, what can we build with the tools that we have? But also, what is the theoretical perfect product look like? So think about it like that, and then saying, okay, now what tools, methods, materials, whatever, do we need to create in order to get the atoms in that shape? But people rarely think about it that way. But it's a powerful tool.
So that's kind of the exercise I want to try to encourage all of you to think about today. Let's see if we can think of a way to take the same types of assets, concrete, steel, whatever we're using today, and rearrange the atoms into something that might be more optimal. So our goal here isn't particularly aggressive. We need something that uses hopefully less than 130 square kilometers of land for safety. Maybe less for noise. Like we don't want to have to acquire thousands of square kilometers of land just for the noise problem. And we want less than a square kilometer building area, less than 900 kilometers of roads, and certainly less than 210 decibels of noise if we can make that all happen. Can we rearrange the atoms to achieve any of those goals? So let's take a look. So the approach that we came up with the Atlantis Project. Now the Atlantis Project is the organization that's responsible for developing a technology called the Tethered Ring. How many people here are familiar with the Tethered Ring? Just so I can... Was that from this morning's or yesterday's presentation? All right, so maybe I have to do a quick explanation because only a few people put their hands in today. The Tethered Ring is a structure that you can build on the side of the Earth, or let's say you can build it in the Pacific Ocean. And think of it as a large ring. It's a pipeline shaped like a ring. You put it in the ocean, and then inside this ring, you have to put a maglev containment system, and then inside this pipeline, I should say, you put a maglev containment system, and inside the pipeline, on that system, you have to have another ring that spins around. Now, the point of this inner spinning ring is to create an inertial force that makes the ring rigid. So you've got this thing in the ocean spinning around and it's rigid. Then what you have to do is attach tethers from the ring to the Earth on the side of the Earth that sticks through the ring. So if you imagine a globe and you turn it so the Pacific Ocean is the top and you put a ring on top of it, say a steel ring, then attach tethers between the edge of the steel ring and points on the globe above it, and then tighten up all these tethers, you could lift that ring off the surface of the globe, if you can imagine that in your minds. This is the idea of a tethered ring. It's an idea that you can build a structure in the ocean and you can lift it up into the stratosphere by pulling on tethers, by tension. So there's no magic, no special physics needed here, no special materials are needed. It can be done with things that are available today. So that was what I was explaining yesterday, and one of the reasons you would build this is because it provides a very interesting energy solution for a carbon neutral economy. But there's many other applications. And one of the applications is to do with space launch, and that's what I was going to talk about in this section. If you want to learn more about the tethered ring, I recommend just go onto YouTube or Google and search for tethered ring, and there's lots of good videos that explain how it works. This is the picture of it, by the way. You get to see a small section of the tethered ring. Actually, I didn't bring my laser pointer, but right here. That's the tethered ring. The launch system that I'm proposing is basically something where you start off in the ocean and accelerate inside an evacuated pipeline up to close to orbital velocity, possibly. Maybe initially we'll go to something below orbital velocity, but you go up to at least orbital velocity in this ring on the ocean. And then you travel up through an evacuated tube that's supported by the tethered ring up to an altitude of, say, 32 kilometers, depending where we put the ring. And then from there, you can travel through the rest of the atmosphere. These two dots represent where the end of the acceleration phase occurs, and then there's a ramp from this red dot, where the red arrow is, to the green dot. So that's the point where you're on the land still, but you're ramping up to start vectoring towards space. And then from the green dot up to the edge of the ring, you're inside an evacuated tube, traveling without air resistance, and obviously without burning up. And then after that, you're traveling through the rarefied atmosphere, upper atmosphere. Here's a picture of what it would look like from right above the launch system, so you can sort of see that you're underneath the tethered ring at this point. This is what it looks like from the exit of the launch system. You exit the vehicle. As soon as the vehicle exits the launch system, it does fire a rocket engine. The rocket engine is used to help maintain its speed as it goes through the atmosphere. It only stays in the atmosphere for a few seconds, I think that's about a minute before it's completely in space. The chart is a chart of all the kinds of things we've done in terms of hypersonics. So on the x-axis is the velocity, and on the y-axis is the altitude. And these are examples of different things that have traveled at these speeds at these altitudes. So you've got on the bottom right a lot of test vehicles that have hypersonic test vehicles of various kinds. There's a table in the corner there. On the left, sorry, the bottom left. On the right side is the Chelyabinsk superbolide, the meteor that came in. That's the velocity trajectory that it took. There have been past proposals for these sorts of launch systems. One's called Skytram, and they were proposing, those red arrows in the middle are what they were proposing they would do, is to start, you accelerate and then start from these altitudes and these speeds and head off into space. The tethered ring is the thicker dark arrow, the black arrow. The region where hypersonic glide vehicle research is occurring, I believe, is in the blue square. And then there's some Air Force studies that were purple line is showing that it was possible to travel at those speeds, those atmospheres for a launch system that was based on an airplane. So lots of different data points around what we can do in hypersonics. And the point is to show that this proposal is in the space of other things we've done. It's building on heritage technologies. All right, so the other interesting part about a launch system is this mass driver idea. Now, mass drivers have been around for a while. Even Gerard O'Neill built one. The challenge with mass drivers that use magnetic coils, kind of like the Navy has these on one of the newest aircraft carriers. The Gerald Ford aircraft carrier has an electronic launch system to accelerate the aircraft. The problem with these is that the magnets have to switch faster and faster the faster you go. So as you start going up to the speeds that we need, the switching times for these electromagnets gets very short, and the power that has to go through each of them goes up, and it creates kind of a greater than square rate of cost. Maybe it's, some people argue it's a cubic rate. So the cost of this launch system goes up with the cube of its length, which is not a really great situation to be in when you want to make a very long launch system. It gets very expensive. So we were thinking, how can we avoid this problem of having these magnets that switch on and off very fast because of limiting our ability to accelerate things? And the idea we came up with was to use, still use magnets, but magnets that don't switch. So these magnets are on the backs of these little arms that you can see. So basically what we have here is a tube that's evacuated, a sled that runs on some tracks, the vehicle sits on the sled, and then there's these twin screws. And the twin screws are variable pitch. And the arms on the sled attach to the screws with electromagnets, similar to the way a magnetic bearing works. They don't touch, but they hover right above the back of the screw, the back of the screw blade. Now this is the very first diagram we did in a very early pitch. We've refined that since. This is a diagram, or more of a simulation of what this looks like. There's actually, it turns out you need to have many of these magnets behind the screws. And the screws will change in pitch, and the rate of, this is running about 1/100th of real time, so the speed that these screws are turning is much, much faster than what you're seeing here. But they're all electromagnetically driven with motors inside. There's no fast switching magnets, they're all running at a constant speed. It's at a reasonable speed for an electric motor. And essentially this thing will move along. By the way, the arms that connect the magnets to the sled are not drawn in here. That's something that wasn't ready at the time this was made. But if you can imagine, there were arms connecting this sled, which is the slab in the bottom, to the green things, which are the electromagnets behind the magnet screws. This system can gradually accelerate you faster and faster. And it can get you up to orbital velocities without having that exponential increase or cubic increase in cost happening, which makes this whole idea of a mass driver much more technically and economically feasible. So here's another close-up diagram showing the magnets, which are the green things, behind the screw flights. Now, one thing to note, you might notice, is the magnets have to reposition themselves occasionally because the screw flight's geometry changes as you advance down the track. All right, well, to support this effort, we've got a digital twin, which is a simulation that models all this stuff. What you just saw was done inside the digital twin. It does a lot of the math and economics around the ideas of the Tethered Ring and this launch system, and spits out numbers, like something like 600 numbers that are spat out of this digital twin that you can examine. It's freely available on GitHub, and you can sort of check the math yourself if you're inclined to do that. This also has some graphs showing how the launch system works, but I don't want to explain that today. There's a lot of parameters that you can adjust if you want to change the assumptions. If you feel there's some technology in there that you know about that we don't know about, adjust the number because of that, because of your knowledge, and see if it helps us out. We're also trying to create a smaller version of this that we're going to put up on to the 3GS website, which is what this drawing is showing. We decided to do it over Hawaii, even though I don't think we can get the Hawaiians to agree to that. But the launch system over Hawaii would be a really good idea, because the mountain up there, that's Mount Hawaii, Kauai. That's hard to pronounce. Pardon? Mauna Kea, right, yeah, that's the mountain. That's a really tall mountain in a fairly low latitude location, really good. So what is a digital twin for? Well, we use it to check the math and avoid mistakes that we might make. We also use it to communicate imaging through images, video clips, and graphs, and to refine the ideas. Once you've seen something in action, you can often go, we could do better. Something about it doesn't look right, it helps you fix it. And now if you were interested in getting involved in this, there's some reasons why you might. Like if you're into programming, you'd be exposed to a lot of interesting techniques that we use in the digital twin, and so that will be a valuable way to gain experience in the field of programming. So I talked about some of the things we use here: dynamic allocation of models, techniques for rendering things at planetary scales. So we have video export and capture features, ways of importing to Google Earth, things like that, and a VR mode. And if you're starting out, this is really good for your resume. But if you're kind of more like me, you're spending a lot of time in industry and you want to kind of enjoy what you're doing, and just want to add benefit to the world, well, this is a good way to do that, because we're trying to find a way to, like I said, rearrange the atoms to make a better solution for getting humanity into space in a sustainable way and in a much more cost-effective way than using chemical rockets, which we've been doing over and over again for many, many years. Thank you very much. All right, any questions?
You're the first fresh idea in that regard that I've seen in I don't know how many years, but quite a few.
Oh, thanks very much. Yeah. Oh, come on up.
Yeah, and with regard to what infrastructure we're going to need for Starship, I'm pretty sure that SpaceX is planning to go to sea,
It's going to.
the ocean.
Yes, yeah, I agree.
Yeah.
Yeah.
So they're not going to need all that land.
Yeah, I agree. Yeah.
And I think your cost chart is a little misleading. The reason that Falcon costs tonight per pound to station are higher, or they're higher than they should be, because they're not taking action on payload, because they're dollar limited. Because they're delivering stuff like, clean clothes and things.
Right.
Because they could have lower cost per pound if they could put more pounds.
Yeah. Well, so on this particular chart, it was possible to get the cost per, or the manifest for the different launch payloads for some of the launches, mainly the cargo launches, but for the crewed launches, for some reason, NASA doesn't want to publish that information. I guess the astronauts don't want their weights online or something. So for those ones, we just put the maximum payload that the system can support according to the data sheets we found.
I'm curious, what is the smallest possible tethered ring that could be created as a proof of concept?
Yeah, so the question is, what's the smallest possible tethered ring that we created as a proof of concept? So we have something called a stepping stone business idea, and we're trying to make a ring that's for energy storage. Now, so it would be like a flywheel, but it turns out the economics of the flywheels are limited by the strength of their materials. With a tethered ring that's magnetically confined, you can get larger and get more energy density with the same material. Now we're exploring how big this ring needs to be for it to be economically viable compared to, say, lithium-ion batteries and other energy storage technologies. We're thinking about around 100 meters is where it would actually become economically viable, depending on how well we can construct magnetic confinement. So I think the proof of concept you're talking about is going to be in this energy storage ring, which will be about 100 meters in diameter. I don't know if it's going to be that would be the MVP diameter or not, but it's going to be in that range. It might be a kilometer, but hopefully that's the size. As for one that's actually off the surface of the Earth, it actually gets cheaper the bigger the ring gets. So if you make the ring smaller, the tethers have to be stronger and thus thicker, and actually the costs start to go up because you don't have as much leverage. The planet's not protruding through it as much. So you kind of have to go big on the ring, the real ring. Next question.
I'm curious how this stacks up against the classic orbital ring by Paul Birch.
Yeah.
What do you say the pros and cons are versus that?
Yeah, so the main, a few cons with the orbital ring approach. The first is that the concept is designed to be launched into space and built in space, so that just get it started up, you need to have rocket launches. This concept is designed to be built on the side of the planet and then lifted away from the planet, so no rocket launches are needed. But the other issue with the Paul Birch approach is that it's not actually a ring. It's kind of more like shaped like a football. With at each end there's a sort of a short space elevator that takes you to the ground. And as a result of this oblong shape, the mass stream inside it has to expand and contract as it travels around in a circuit. And because of this expanding, contracting mass ring, this creates a situation where you need expansion joints or individual discrete pellets or something to travel in the loop. And when you create these expansion joints in a mass stream, it makes it non-uniform. And when you make it non-uniform, it's much harder to make a containment system work with no magnetic friction. So when you have changing things traveling through a magnetic field, the magnetic field creates eddy currents and any metals in there, and it slows it down. So that's kind of a fundamental flaw in that design. Now he talks about dealing with it with magnetic shielding. He's sort of aware of the problem, but he didn't really go into any detail. The tethered ring solves that problem architecturally. It's a uniform ring, not oblong, it's perfectly circular, traveling through a magnetic field that's perfectly homogeneous. So it's a bit more like something traveling in orbit around a small moon than only it's not gravity is holding it in, it's a magnetic field. That was a long answer, sorry. How are we doing for time? I want to make sure we're not cutting into your session.
Question.
Oh, we are cutting in by 2 minutes, I'm sorry.
Not a problem.
All right, I have to,
Ready to
can't take
finish
any more.
your-
No, I think we're done with questions. I didn't see any more hands, so
That's one quick one.
Very quick.
What direction does it go?
what direction does it go?
Yeah.
Oh, the launch system?
Yeah.
Yeah, it can go any direction, obviously, but I'm thinking the optimal thing is to launch in the same direction the Earth is spinning. And
That's the equation.
you get the advantage of it doesn't have to be the equator, but the closer the better.
Well,
It's just like any other launch site.
That's going to determine your inclination where you want.
Yeah, so actually, it'd be interesting to see how hard it will be to do orbital inclination changes later, right? So, yeah, that would be one of the aspects of this technology is that when you go into infrastructure, you're sort of fixed on a certain inclination because you've invested in the infrastructure for that inclination. And if you want to change inclinations, you got to figure out a way to do that.